Right now, a fleet of NASA spacecraft are turning their attention to an unusual object.
This is an object, if that is the size of it, that is 1,000,000 times more massive than the previous interstellar objects we've seen, and that's quite unlikely. There is not enough material in interstellar space.
Each interstellar visitor we've recorded looked different. Different shape, different behavior, different timing.
NASA scientists say it's a comet. It could be alien technology. You heard that right. So, does this mean ET is real?
It's moving at a velocity of about 135,000 miles per hour, so it's going really fast.
At first, that made them feel like rare accidents. But when AI analyzed all three together, the focus shifted fast. The problem wasn't the objects, it was us. The first two interstellar visitors. On October 19, 2017, the Pan-STARRS 1 telescope in Hawaii spotted a tiny moving dot that did not fit the usual pattern. At first, it looked like a normal speck, faint, fast, easy to miss. Then the orbit checks came back, and everything changed. The path wasn't a closed loop around the sun, it was an open escape route. Whatever this thing was, it was not from here. People later called it 1I 2017 U1, but it also got a nickname that sounded like a warning label, Oumuamua. It was a Hawaiian name meaning a scout, a messenger that arrives first from far away. By the time scientists realized what they were looking at, it was already leaving. It had swung past the sun on September 9, 2017, then kept going. And at its closest to the sun, it was moving at around 196,000 miles per hour. So telescopes everywhere piled in, because there was no second chance. And almost immediately, Oumuamua started acting in ways that set off arguments among scientists. Not because it was loud, because it was quiet. No beautiful tail, no obvious fuzzy cloud around it. ESO said it looked completely inert, with no hint of dust around it. That no tail detail matters because comets usually look messy when they get warmed up. Ice turns into gas, gas drags dust off the surface, and suddenly you get that classic bright fuzz and tail. Oumuamua didn't give us that. Then came something else. Over just a few days in October 2017, the brightness kept swinging up and down in a way nobody expected. It varied in brightness by about a factor of 10 as it spun, and the spin cycle was about 7.3 hours. Bright, dim, like a long, uneven object flipping over and over while sprinting away from us. NASA tied that wild brightness swing to shape. The simplest idea was, it must be extremely stretched out, roughly 10 times longer than it is wide. NASA even said it could be up to about 1/4 of a mile long, which is already strange to picture. Something that long, but maybe only a fraction as wide, drifting through space like a splinter thrown into the dark. And this is where it gets more unsettling. The most elongated objects we had seen before were no more than about 3 times longer than they are wide. Oumuamua wasn't in that league. It was in a different sport. It also didn't spin neatly like a top. It was tumbling, flipping end over end while also rotating on another axis. Then there's the, how long was it out there? Gut punch. Observations suggested it had been wandering through the Milky Way, unattached to any star system, for hundreds of millions of years before it stumbled into ours, and the distances were already getting brutal. By November 20th, it was about 124 million miles from Earth, already fading into the dark. It was heading toward the constellation Pegasus. People even tried to give it a kind of return address. Its incoming path pointed roughly toward the bright star Vega, with an important catch. Over huge stretches of time, stars move. Vega today is not sitting in the exact place it would have been when Oumuamua was still far away. By itself, the shape and speed would have been enough to make Oumuamua famous. But then it pulled its most annoying trick. It didn't fly like a dead rock should. After weeks of tracking, researchers reported that it was moving away from the sun faster than predicted. ESA and Hubble described this as anomalous behavior, and said the data suggested it was more likely a comet than an asteroid, even though we never got the classic comet tail on camera. By early 2018, the first visitor was gone, leaving behind a strange feeling. Something had just blown through from another star system, and we barely caught a glimpse. So when the next thing came out of the dark, everyone was ready. Less than 2 years later, the universe sent a second visitor, and this one showed up wearing a disguise humans instantly recognized. On August 30th, 2019, a Crimean amateur astronomer named Gennady Borisov was scanning the sky with a homemade telescope when he noticed an object moving in an unusual direction. After about a week of observations by astronomers around the world, its path was locked in. This one came from outside our solar system too. The name was blunt and perfect. 2I Borisov. Unlike Oumuamua, Borisov didn't hide what it was. NASA's Hubble Space Telescope took images in October and December of 2019, and those images showed lots of dust around a bright nucleus, even though the nucleus itself was too small for Hubble to see directly. That dust mattered because it meant the object was active. And even though Hubble couldn't see the nucleus directly, NASA says the best guess is that the core is a loose clump of frozen ices mixed with dust, basically the same kind of rough, crumbly build we see in comets from our own solar system. The difference is, this one did that whole trip between stars before it ever met the sun. Its speed was still wild. It tore through the solar system at about 110,000 miles per hour. The sun could tug on it a little, bending its path, but it could not hold on. Moving that fast, Borisov was never going to stay. Its size was about 3,200 feet across, roughly the length of 9 football fields laid end to end. It wasn't a planet killer, but it was big enough to carry a serious load of ice and dust, and big enough that its chemistry could tell a story about where it formed. Borisov reached its closest point to the Sun on December 8, 2019, at a distance of about 190 million miles. Close enough to heat it up, but not close enough to burn it away. Hubble checked in right after that close Sun pass. On December 9, 2019, Borisov was seen racing along at about 100,000 miles per hour. Later that same month, it made its closest approach to Earth, passing at roughly 180 million miles away. So if Borisov looked like a normal comet, why did it turn into a headline object? Because its chemistry refused to behave. In April 2020, NASA described a moment scientists live for. They aimed a powerful radio observatory at Borisov and listened for the fingerprints of gases coming off the comet. The instrument doing the sniffing was ALMA in Chile. It is a radio telescope made of 66 dishes working together, which is perfect for picking up cold, low-energy gases. And when the team looked inside that gas halo, they found something they did not expect to find at that level: carbon monoxide, in a huge amount compared to other gases. Carbon monoxide is a simple gas made of one carbon atom and one oxygen atom. It freezes easily in deep cold and turns into gas quickly when warmed. And with Borisov, the amount of carbon monoxide was estimated to be between 9 and 26 times higher than what we see in comets from our own solar system at the same distance from the sun. There's a reason that hit like a plot twist. A comet can look normal on the outside: dust, coma, all the classic signs. But the gases it releases are like a recipe card. Borisov's recipe looked different. There were still grounded ways to explain it. Maybe Borisov formed far from its star, in a colder zone where carbon monoxide ice could stay locked in. Maybe it's a fragment from a larger icy body that had carbon monoxide closer to the surface. Or maybe it has a thick outer layer that keeps other gases frozen longer, making carbon monoxide stand out because it escapes first. And Borisov did one more thing that made it feel alive. In March 2020, Hubble spotted a clear change. Instead of a single bright core, part of the nucleus had broken away. This object traveled between stars, crossed into our solar system, started shedding gas and dust, and then began to break apart on camera, like it couldn't handle the heat of a new sun. And then the next visitor showed up, and this time, the solar system was already watching. The third interstellar visitor. On July 1st, 2025, a small survey telescope in Chile did what it was built to do. It flagged a faint moving dot that did not belong where the stars said it should be. The system is called ATLAS, short for Asteroid Terrestrial Impact Last Alert System, and NASA funds it as an early warning network for space rocks that could get uncomfortably close to Earth. This time, the alert wasn't about a future impact. It was about a stranger. At first, it was tagged as a maybe, the kind of object that usually fades away once follow-up data rolls in. But this one did not fade. Then the orbit math locked in, and the name became Comet 3I Atlas. 3I simply means it was the third confirmed interstellar object. What makes this third visitor feel different is how fast everything came together. Scientists didn't have to wait weeks to figure out whether it was real. They went back through older images from other sky surveys and found the same small speck sitting there unnoticed. It showed up in archived pictures from 3 different ATLAS telescopes and from the Zwicky Transient Facility, pushing the timeline back to June 14th. That meant the object had already been heading our way for more than 2 weeks before anyone officially noticed it. Once the orbit was locked down, the interstellar part was easy to understand. Its path was hyperbolic, which is just a technical way of saying it was not trapped by the sun. It wasn't looping around or settling into an orbit. It was passing straight through on a one-way path, driven by its own speed and only bent slightly by gravity as it moved past. That kind of trajectory is exactly what you expect from something that came from outside the solar system and is not coming back for another pass. Then came the first clear answer to the big question: What is it? And the answer was straightforward. This was not a dead rock. It was active and surrounded by a coma. A coma is the fuzzy cloud of gas and dust that forms when sunlight warms ice, and the ice starts releasing vapor, dragging dust along with it. Put simply, it was heating up as it came in, and that activity gave it the familiar look of a comet. Even the direction it came from feels interesting. It approached from the direction of Sagittarius, a known patch of sky that points toward the dense central region of the Milky Way. When Atlas first detected it, the object was already about 410 million miles from the Sun. That is far beyond Earth, but still inside Jupiter's orbit. At the time it was discovered, it was moving at roughly 137,000 miles per hour. As it dropped deeper into the Sun's gravity, it sped up even more, reaching about 153,000 miles per hour at its closest pass. The object posed no danger to Earth. The closest it was expected to come was about 170 million miles on December 19, 2025. That is an enormous distance. But by space standards, it is still close enough to study in detail if you have powerful instruments and accurate tracking. Limits based on Hubble data place the nucleus, the solid icy core, somewhere between about 1,400 feet and about 3.5 miles across. That is a huge range, not because anyone was guessing, but because the comet was wrapped in a thick cloud of dust that blocked a clean measurement. Even with that problem, Hubble still delivered a striking view. On July 21st, when the comet was about 277 million miles from Earth, it did not appear as a neat round object. It looked wrapped in a teardrop-shaped shell of dust. A plume could be seen streaming off the side facing the sun, along with the early hint of a tail. One smaller detail made those images even more interesting. The rate at which the comet was losing dust matched what scientists usually see from comets first observed at around 300 million miles from the sun. Hubble did not stop after one set of images. It observed the comet again on November 30th, when it was about 178 million miles from Earth. The setup was the same. The comet stayed sharp, the stars smeared into lines, and the images gave the strange impression that the sky was moving because the telescope had to chase the object to keep it centered. This time, it was not just one observatory with a few follow-ups. It turned into a coordinated effort. Multiple missions and telescopes joined in, because everyone understood this was a one-time visitor that would disappear back into interstellar space. The James Webb Space Telescope was brought in early. On August 6th, it observed Comet 3I Atlas using the near-infrared spectrograph. The idea behind that instrument is simple. It breaks the comet's light into patterns that can reveal the types of gas and dust surrounding it. A newer space telescope joined soon after. SphereX observed the comet from August 7th through August 15th and released its own early findings. SphereX works in infrared light, which is especially good at detecting warm dust and certain gases that are harder to see in visible light. That meant Webb and SphereX were looking at the same target in different ways at the same time. Even missions built for completely different purposes were pulled into the effort. The Psyche spacecraft tracked the comet on September 8th and 9th, collecting images over about 8 hours while the object was roughly 33 million miles away. Psyche is headed toward an asteroid, but its cameras still helped refine the comet's position and appearance while it was still inbound. Lucy, another spacecraft already on a long journey, also joined in. On September 10th, Lucy captured images from about 240 million miles away. Just aiming the spacecraft was a challenge. Lucy had to point closer to the sun than it normally does, and the team had to carefully manage heat. Ground-based telescopes backed this up as well. Lucy's observation window lined up with the Las Cumbres telescope network on Earth. Observing from two very different locations helped track how the comet's dust and gas changed over time. Having multiple viewpoints reduced the risk of misreading what was actually happening. Mars ended up with one of the best seats. In early October, the comet passed within about 19 million miles of Mars. That is still far by everyday standards, but close enough in space that orbiters around Mars captured some of the clearest images obtained. The Mars Reconnaissance Orbiter spotted it, and other Mars missions added their own observations. The period around its closest pass to the Sun became its own waiting game. The comet stayed visible to ground-based telescopes through September, then moved too close to the Sun to be observed clearly. Even while it was hidden, attempts to track it continued. The sun-watching SOHO spacecraft captured images between October 15th and October 26th from about 222 million miles away. SOHO sits roughly 1 million miles closer to the Sun than Earth and constantly watches that region. Since launching in 1995, it has discovered more than 5,186 comets. All of these observations served a practical purpose. As comets heat up, gas escaping from their surfaces can slightly alter their paths. With something moving this fast, even small changes matter. The observed shifts were minor and matched normal comet behavior. which was reassuring in its own way. A visitor from another star system behaving just like a comet should. Then AI analyzed all 3 visitors together, and something scary showed up. The scary truth behind these visitors. The unsettling part is not what those 3 visitors were. It's what they proved about us. The first 2 did not even resemble each other. They differed in almost every measurable way. That is not a fun fact. It is a warning. If the only 3 confirmed visitors so far can look that different, then the next one could arrive looking nothing like what we expect. Here is where it gets uncomfortable. Objects like the first visitor may pass through the inner solar system about once per year. But they're faint, hard to spot, and were being missed until survey telescopes got powerful enough to have a real chance. The sky didn't suddenly become busy. We just got better at noticing how busy it already was. The pattern is that the universe can toss stuff through our neighborhood more often than our brains want to accept. And most of the time, we only catch it when luck and timing line up. And timing is the cruelest part. The system we've built for early warning is mostly built for near-Earth objects, asteroids and comets that orbit the Sun and come within about 30 million miles of Earth's orbit. It's basically a neighborhood watch for space rocks that keep coming back around on repeat routes. Interstellar visitors don't play that game. They don't do slow, repeat loops. They don't give you a long, calm schedule. They punch in, they cut across, and they're gone on a one-way exit. So even if you have a decent neighborhood watch, that watch is still aimed at the wrong kind of problem. One major limitation is night. Data can only be collected at night, and even then, the weather can shut everything down. Bright skies, clouds, smoke, or haze all cost time. If conditions are bad, observations stop. Speed makes that worse. Because these objects move across the sky, exposures are limited to about 30 seconds. You do not get long, relaxed observations. You have to capture the light quickly, before the object smears into a streak and becomes harder to identify. Those 2 facts mean the net we throw over the sky has large gaps in it, even when everyone involved is doing their job well. And then there is the biggest blind spot of all, the Sun. Detecting objects near the Sun, or coming from its direction, is extremely difficult, and sometimes nearly impossible from Earth. There are asteroids hidden in the Sun's glare that we cannot track, and some of them could be on paths toward Earth without us knowing. That blind spot matters for normal asteroids. For interstellar visitors, it is worse. They can arrive from almost any direction. If one comes in from the sun-facing side, it can remain invisible until it crosses into the night sky. By then, the best part of the encounter may already be over. There is another problem layered on top of that. The visitors we do detect are probably not typical. They are the easiest ones to see, the brighter ones, the ones that pass through parts of the sky that our surveys are already watching. This is where the fear starts to make sense. What happens if one is dangerous? If an object is hard to detect and does not follow a predictable orbit, then the window to react is small. You do not get years of tracking. You do not get time to debate or plan. You get a brief opportunity, and whether you catch it depends on the weather, timing, viewing angle, and whether the right instruments are looking in the right place. That is why the next phase is not, maybe we see one again in a few decades. It is about volume. The Rubin Observatory has been clear about this. Scientist Michelle Bannister says the goal is to move from studying a couple of objects to studying dozens. The observatory is designed to take about 1,000 images of the southern sky every night, covering the entire visible southern sky every 3 to 4 nights. In doing that, it expects to find millions of previously unseen asteroids, comets, and interstellar objects. There is a quieter consequence most people overlook. Once you watch that much sky that often, the main problem stops being detection and becomes sorting. Rubin is built to generate an alert stream. Every time something changes or moves, it sends a signal. The system is expected to produce around 10 million alerts per night, with each image generating about 10,000 alerts within roughly 1 minute. No human can manually review that volume. It is not possible. That means computers filter first. They rank events, flag anomalies, and surface the odd ones. That is the only way future interstellar visitors will be recognized quickly enough for coordinated follow-up. When that system turns on fully, we will not just get better at spotting visitors, we will also learn how many were always passing through unnoticed. Detection rates could rise from a few interstellar objects per decade to potentially 1 every few months. Even with Rubin, even with better software and more coordination, gaps remain. The sun's glare does not disappear. Weather still interrupts observations. Objects still move too fast for long exposures. These are limits that do not go away. That is why space agencies are pushing for new observing systems. NASA's NEO Surveyor mission is designed to detect objects using infrared light, which helps reveal objects approaching from the sun's direction. The European Space Agency's planned NEOMIR telescope is aimed at the same problem. Positioned between Earth and the sun, it would scan the daytime sky for heat signatures. Thanks for watching. Now check out the videos popping up on screen for more unbelievable stories.